Hello guys, and welcome to the second part of this tutorial, which is on functions. In this particular tutorial, we will be looking at rational functions. We will study the functions directly. Secondly, we'll study the functions from the variation tables. And thirdly, we are going to study these rational functions from the graphs of this function. Please stay tuned to the end of this video and don't forget to leave your comments and your likes, as a lot of material is going to be dished out to you here. Stay tuned and welcome to the GCE Maths Panel. This copy is copyright protected. So the first question is, this function, we have x on x minus 1, which is a rational function. First of all, you have to understand that the rational function, in simple terms, is a function that has x in the denominator. So if there is no x in the denominator, you cannot call that function a rational function. There might be no x in the numerator, or if the function is in x, there might be no variable in the numerator, but if there is no variable in the denominator, it is not considered a rational function. So for a function to be a rational function, there should be a variable in the denominator. These are the type of functions we are looking at. So let's study this function starting with the domain of definition. Don't forget to subscribe and to leave your likes below. So the domain of definition of this function is a set of all real numbers excluding 1. Now we know that for a rational function, if the denominator is equal to 0, that function will be undefined. So what we are going to do here is we are going to inequate this denominator to 0. That means the denominator should not be equal to 0, and we solve for x. So the set of all real numbers excluding 1 is the domain. In interval notation, this can be written as from negative infinity to 1 from below, and from 1 from above to positive infinity. This function therefore has 1, 2, 3, and 4 bounds. There are 4 bounds in the domain of definition of this function. Now that you have the domain of definition, the next thing about this function is to get the limits at these bounds of the domain of definition. And for rational functions, we just have to, at infinity, I repeat, at infinity only, we take the term with the highest degree in the numerator and divide by the term with the highest degree in the denominator and substitute infinity in that. Let's see what we do. So as x tends to plus or negative infinity, this is a particular case, like you saw in one of our chapters. If the limits are the same, you can combine the limits. So as x tends to negative infinity, the highest degree in the numerator is x, highest degree in the denominator is still x. And so x divided by x gives us 1. So the limit as x tends to a constant of the limit of a constant is equal to that same constant. So as x tends to negative infinity, this limit is equal to 1. Equally, as x tends to positive infinity, we are going to have the same value. That is why we have combined these two limits into 1. Now, the limit as x tends to 1 from below, we can take a number very close to 1, like 0.9. We test. We know that x equals 1 is a vertical asymptote, because this function is not defined when x is equal to 1. In that case, x equals 1 is a vertical asymptote. And whenever you take limits at a vertical asymptote, that limit is infinity. So now we are taking limits as x tends to 1 from below. That means slightly below the vertical asymptote. We want to know the type of infinity that we have, that is in layman's terms. Is it positive infinity or negative infinity? So these numerical values we are using to test is to get the sign of that infinity, because we already know that the limit that as x tends to 1 is equal to infinity. But now we need to know the sign. So as x tends to 1 from below, you can write this less than sign or put negative after. We take a number slightly less than 1. So I advise take a number like 0.1 units less than. So 0.9 in the numerator over 0.9 minus 1. So you can see that the numerator is positive and the denominator will be negative. The combined division will give us a negative sign. So this limit is negative infinity. Why negative infinity? Because we are taking limits at 1, slightly less than 1. Okay. Now the other limit of x tends to 1 from above, we take a number slightly greater than 1. We know that 1 is still the vertical asymptote, so the limit is going to be infinity. But now, is it positive for infinity or negative infinity? So we take a number slightly greater than 1, for example, 1.1, and we substitute in this given function. We are going to have 1.1 divided by 1.1 minus 1. The numerator and denominator are both positive, so the result is positive. And since we knew that this limit was infinity, the result is positive infinity. In this particular case where we have taken the limits as x tends to positive and negative infinity and the value is 1, this tells us that the value of y equals 1 is the equation of the horizontal asymptote. Horizontal asymptote. So now let's move on to get the asymptotes. You can get the vertical asymptote from the domain of definition. We already mentioned it. X should not be equal to 1. You can see it in the domain. X should not be equal to 1. So x, in that case, x equals 1 is a vertical asymptote. Don't use not equal to the vertical asymptote, just equal to. You use not equal to, but for the domain. Now, the horizontal asymptote is the equation y equals 1. That's the horizontal asymptote. We get the vertical asymptote from the domain. We get the horizontal asymptote from the limits. Vertical asymptotes from domain, horizontal asymptotes from limits. And we can equally talk about the center of symmetry of this curve if these two asymptotes exist, which is defined as the vertical asymptote, comma, the horizontal asymptote. That gives us the center of symmetry. So if y was equal to 2 here, the center of symmetry will be 1, 2. Okay. Now let's talk about the intercepts. As x turns to 0, or when x is equal to 0, what will be g of 0? G of 0 is going to be 0. So we have an intercept at the point 0, 0, which is the origin of the Cartesian plane. Now, when x equals 0, y is 0. So I cannot talk again about if y equals 0, because from here we can see that when y is 0, x is also equal to 0. This brings us to the gradient function. And since this is a rational function, we are going to be applying the quotient rule. You know what the quotient rule is about, right? So for the quotient rule, we have the bottom constant to differentiate the top, minus the top constant to differentiate the bottom, all that on the square of the bottom. Again, the bottom constant, the bottom is x minus 1. We differentiate the top. When you differentiate the top, you're going to have 1, minus the top constant, the top here is x. You differentiate the bottom, you're going to have 1, all that on the square of the bottom, or all that on the bottom squared. So that gives us all that on x minus 1 squared. When we simplify this numerator, we are going to have x minus 1 minus x, which all together gives us minus 1 all over the square of x minus 1. And observing this, you see that the numerator here will always be negative. And since the denominator is squared, the denominator is always positive. A negative number divided by a positive number is a negative number. This tells us that this gradient function is always negative. So we say it's strictly less than 0. And we conclude that this curve is strictly decreasing. At times, you may be asked in an exam to prove that the curve is strictly decreasing. What you have to do is you look for the gradient function and you show that it is negative, like we have shown here. So in this case, equally, you can see that from this gradient function, there is no variable in the numerator. Look at it, you just have negative 1. There is no variable to solve for. So when you equate this gradient function to 0, there will be no variable to solve for. So there is no turning point. Let me say it in the simplest way that other students understand. There is no x in the numerator of this gradient function. As you can see, there is no x in the numerator. So since there is no x in the numerator, therefore, there is no turning point. Okay? And this function is strictly decreasing because, as I've shown, the gradient function is strictly negative. Now, let's move on to our table of variation. And for this table of variation, just like we saw in the previous lesson, and as we are going to be seeing in subsequent lessons, we have from the domain of definition, we have from negative infinity to 1 from above and below to positive infinity. So this first line occupies that position, negative infinity, 1, positive infinity. There is no turning point. And if there was, I would have included the x value on this first row. And now we equally know that this line x equals to 1 is the equation of the vertical asymptote. So I'm going to put a solid line here to indicate that the curve does not cross the line x equals 1. The curve does not cross the line x equals 1. Equally, from my gradient function here, I've seen that this curve is strictly decreasing. So for this gradient function here, everything is going to be negative and negative, 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 because this is strictly decreasing. Another way to do it is just take any number in this interval from negative infinity to 1, substitute here and see if your answer is going to be negative. It will be from 1 to positive infinity is going to have the same value. Okay, now we are being told that this curve is strictly decreasing. So in this interval, it decreases. Note the curve always decreases from left to right. and here it equally decreases. But it has to decrease from a number to another number. Now, when x is equal to or tends to negative infinity, what is the value of y? You can see this from the limits. As x tends to negative infinity, y was equal to 1. So as x tends to negative infinity, this tends to 1. And as x tends to 1 from below, you can still see this from limits. As x tends to 1 from below, this is it. We had negative infinity. So this curve is decreasing from 1 to negative infinity. Now, as x tends to 1 from above, what did we have for y? 1 from above, we have positive infinity. And it decreases to, as x tends to positive infinity, what did we have? Positive infinity, we had 1. Just by looking at this variation table, you can see that there is a horizontal asymptote. This is the horizontal asymptote. Y is equal to 1. Because the limit as x tends to negative infinity was 1, the limit as x tends to positive infinity is still 1. So it means that you can see here that there is just one horizontal asymptote. If you had something like 1 here, and let me say you had 2 or 3 here, you will know that there are 2 horizontal asymptotes. So from the variation table, you can see the number of asymptotes that the curve has and number of vertical asymptotes. So this curve has just one horizontal asymptote and one vertical asymptote, just like we saw before at limits and at the domain of definition. So if you are starting this curve from the variation table, you can see all of this, okay? And we are going to be seeing that in examples 4, I think 4 and 5 in this particular lesson. You can now sketch a curve. We already have all the parameters. One of the intercepts is at the origin. We have the horizontal asymptote at y equals 1, vertical asymptote at x equals 1. And we know that this curve decreases from 1, that is below this horizontal asymptote, this is decreasing like this, right? It passes through the origin, as you can see, and as x tends to 1 from below, it was negative infinity. So we have this line, as you can see. So this curve passes like this. Then as x tends to 1 from above, it started at positive infinity, as you can see from the variation table. And therefore, it should decrease in this direction, as we've seen like this. All right, you can now link those points. And when we link, this is what we have for the curve of this function, okay? And this is the curve of G, as easy as it is. So here are some remarks. When the degrees of the numerator, I mentioned this in functions, that's chapter 6 on functions. When the degrees of the numerator and denominator are the same, we are going to have a horizontal asymptote that is not equal to 0. The degree here is 1, x to the power 1. The degree here is x to the power 1, has the highest degree. So we have a horizontal asymptote which is not equal to 1, as you can see here. But if the degree of the numerator was less than that of the denominator, we will have a horizontal asymptote which is equal to 0. Here, the center of symmetry is the point 1, 1 as well. And there are 4 bounds, as we saw, 1, 2, 3, and 4 from the domain of definition. All right, guys, don't forget to subscribe and to share this video with your friends. We are moving now to the next question, the second function. Copyright its contents. So second function is this. This is what we're just explaining. If you look at the degree of the numerator here, it is 0. The degree of the denominator here is 1. That's x to the power 1. Here, x to the power 0. In short, the degree of the denominator here is higher than that of the denominator. So just by looking at this function, we are already seeing that the horizontal asymptote is the line y is equal to 0. Y is equal to 0, like we mentioned before. There are 3 cases of horizontal or oblique asymptotes, as we may call them. So from here, the domain 1 minus x should not be equal to 0, otherwise this function will be undefined. So x should not be equal to 1, and our domain will be from negative infinity to 1 from below, and then we continue with 1 from above to positive infinity. And now we can get the limit as x tends to positive or negative infinity. We already mentioned that the limit was going to be equal to 0, right? So you just substitute negative infinity here. You have 3 over negative infinity over negative 1 minus infinity. That's 3 over positive infinity, which is 0. You substitute positive infinity, you are going to have the same thing. So we combine these 2 limits. Now the limit as x tends to 1 from below, we take a number slightly less than 1. We have 3 over 1 minus 0.9. This is going to give us a positive value. So we have the numerator is positive, the denominator is positive. So since x equals 1 is a vertical asymptote, the limit at the vertical asymptote is infinity. So what we are doing here, we are just testing to see the sign of the infinity. And here the result shows that it's positive. As x turns to 1 from above, we take a number slightly greater than 1, 1.1 for example. So we have 3 over 1 minus 1.1. The numerator here is positive and the denominator is negative. So we are interested in the sign, it is negative. We know that x equals 1 is the vertical asymptote, so that limit is infinity, and now we have the sign to be negative. We can now state the equation of the asymptotes. We have the vertical asymptote from the domain of definition. The vertical asymptote is x equals 1, that's that line. And the horizontal asymptote from limits is the line y equals 0. Like I said before, vertical asymptote, you can see it from the domain, and the horizontal asymptotes from limits. Or the intercepts, if x is equal to 0, y will be equal to 3. If y is equal to 0, there is no value of x. So we have just one intercept here. X equals 0, y equals 3. We can now conveniently or move safely to our gradient function. Since it's a rational function, like I mentioned before, a function is considered to be rational if there is x in the denominator. Here there is no x in the numerator. We don't care about that. There must be an x in the denominator, or there should be a variable in the denominator. I'm speaking the language that everybody understands, okay? Good, so keep the bottom constant since it's a rational function, applying the quotients rule, bottom constant, differentiate the top, differentiate the constant, you have 0, minus the top constant, so minus 3, differentiate the denominator, you have minus 1. This way students will make a mistake. They'll forget that it's supposed to be minus 1 and they'll put 1. This way things will get bad enough. All that on the bottom squared. So this gives us, all right, so this gives us 3 over x minus 1 all squared. And from here, you can say the numerator is positive always. The denominator is also always positive because it is squared. And therefore, this gradient function is always greater than 0, or is always positive. Therefore, this curve is strictly increasing, unlike the previous example, which was strictly decreasing. This one is strictly increasing. Now, there is no variable in the numerator of the gradient function. There is no x here, so there is no turning point. So the two things you see here is that for the monotonicity of this curve, the g is strictly increasing on r, and secondly, there is no turning point. And this brings us to a variation table from the domain of definition. We have from negative infinity to 1 to positive infinity. And x equals 1 is the line of the vertical asymptote. So I'm going to put a solid bar here to indicate that this is a vertical asymptote. Now, this gradient function tells us that the monotonicity of this curve is such that g is strictly increasing. So the gradient function is always positive, and therefore means it increases from negative infinity to 1, and also increases from 1 to positive infinity. Now we can get these other values from the limits. As x tends to negative infinity, from limits, what did we have? G was tending to 0, or y tends to 0. This is it. So it increases from 0 to, as x tends to 1 from below. 1 from below, what did we have? Positive infinity. Positive infinity. Positive infinity. As I said before, is you should never have negative infinity up. This is the position for negative infinity. So negative infinity will either be at this position, this, or this. Negative infinity should never be up here, because negative infinity means the smallest value that exists, or it's a description of the smallest value that can exist. So it cannot be up. Something cannot decrease from something that is smaller than something that is smaller than it. So as x tends to positive infinity, as x turns to positive infinity, this also turns to 0 from the limit. And this is what we have. So our curve is now complete, and we can move on to the sketching of this curve. We start by the intercepts. You already have the intercepts. You have the intercept, the horizontal asymptote, which is also equal to the x-axis, or the line y equals 0. Normally, I should use a broken line here, but I've just put this yellow in the exam. Just use a broken line on this axis. Then you equally have the vertical asymptote, which is the line x equals 1. We have an intercept at a point 0, 3. 0, 3. So there's an intercept here, 0, 3. Which I have not yet put. Let me get an intercept and place at that point. All right, so at 0, 3, there's an intercept here. Okay. And then we have, so you can start this curve. In this interval, it's strictly increasing. So it increases above this line, this horizontal asymptote, passes through this intercept to positive infinity. Because you can equally see this, if you look at your variation table, you see how the curve looks like. And equally here, from above, it increases to this direction. We can now link these points. All right, sorry for my calibration here. This calibration, the y-axis is a bit messy. So this is the point 3. Take note of that, please. So the point 3 is here, which I've just plotted. So it should normally be down, not up here. Yeah, these are just some minor errors. And all right, so some remarks for this curve. When the degrees of numerator is greater than the denominator, so when the degree of the numerator, oh my God, the degree of the denominator rather, when the degree of the denominator, here it's supposed to be deno. Let me see, I can adjust this. This pen does not seem to be the best. All right, so in the degree of the denominator, when the degree of the denominator is greater than the degree of the numerator, then the horizontal asymptote is equal to 0, just like we have seen here. The degree of the denominator is greater than that of the numerator. That's why the horizontal asymptote is equal to 0. And this curve has a center of symmetry at the point 1, 0. And the domain has 4 bounds. Okay, we can now move to the next question. If you don't understand this, please, you can look at the question again. We can now move to the next question. All right. Copyrighted content. Now, this is another beautiful one in which the denominator is a quadratic. And looking at this also, you can see that the degree of the numerator is less than that of the denominator. Our horizontal asymptote is automatically the line y equals 0. And from here, we can see that we have 2 vertical asymptotes. And we are going to see how we can get the center of symmetry. When we have 2 vertical asymptotes, how do we get the center of symmetry? So let's start with this curve by looking at the domain of definition. So for this curve, this denominator should not be equal to 0. It means that x should not be equal to 1 and x should not be equal to 3. Therefore, our domain is from negative infinity to 1 from below. Then we continue with 1 from below to 3 from below. I'm sorry, from 1 from above to 3 from below. Then from 3 from above to positive infinity. Negative infinity to 1 from below. 1 from above to 3 from below. 3 from above to positive infinity. So we have how many bounds? 1 bound, 2 bound, 3 bounds, 4 bounds, 5 bounds. So we have 6 bounds in this curve. So we are expected to have 6 limits. But we already know the limit as x tends to infinity, whether positive or negative is 0. So I can combine these 2 limits at the bounds, the first and the last bounds. And this gives me 2 over infinity, right? That's 0. Then the limit as x tends to 1 from below. We know that that limit is actually infinity, so we can test for the sign as x tends to 1 from below. Take a number slightly less than 1. Numerator will be positive, 0.9 minus 1. This one is going to be negative. Negative times negative is negative. It is positive. So positive divided by positive gives us positive. That's why this limit is positive infinity. The limit as x tends to 1 from above, we take a number slightly less than 1. The numerator is positive. This first bracket will be positive. Second bracket is negative. Negative times positive is negative. And this positive divided by negative is negative. So we have negative infinity here. The limit as x tends to 3 from below, we do the same thing. We have negative infinity. And as x tends to 3 from above, we have positive infinity. Now we can state our asymptotes. How many vertical asymptotes we have? We have 2 vertical asymptotes. These are the 2 vertical, x equals 1 and x equals 3. You can see that from the domain of definition. The horizontal asymptote from limits is y equals 0. Now the center of symmetry, since we have 2 vertical asymptotes, the x value of the center of symmetry will be the average of these 2. It is going to be the average of these two. So is this value here correct with the center of symmetry? Of course, the value is not correct. So because of that, this average now therefore gives us x, which is 1 plus 3 divided by 2, that gives us 2, and we have 0 at this point, okay? Now we can equally get our intercepts. The intercepts when x is equal to 0, we are going to have 2 on 3 as the y value. So we have just one intercept here, because if you solve the equation y equals 0, we are not going to have any values for x. Gradient function, this is a quotient function, so we are going to use the quotients rule. When we apply the quotients rule, we are going to obtain this. You keep the bottom constant, that's x minus 1 to x minus 3 constant. Differentiate the top, you're going to have 0, so no need writing this one. Minus the top constant, so I just started at minus 2 constant. Differentiate the bottom. When you differentiate the bottom, this quadratic, when you differentiate all of this, you're going to have 2x minus 4. All this on the bottom squared. All this on the bottom squared. And when you equate this to 0 and solve for x, we are going to see that the value of x equals 2. This is already telling us that there is a turning point. So we now look for the corresponding value of y when x equals 2. So g of 2, for g of 2, we use this function. When x is equal to 2, you have 2 over 2 minus 1 into 2 minus 3. That's going to give us minus 2. So with this particular curve, there is a turning point at 2 minus 2. There is a turning point for this curve at 2 minus 2. Okay, and then from this gradient function too, we cannot say whether it is increasing or decreasing. Therefore, means there are intervals in which this curve is increasing and others in which it's decreasing. Unlike the previous two that we saw that they were strictly increasing or strictly decreasing. With this particular case, there is x in the numerator. So there are intervals in which this function is increasing and there are intervals in which it is decreasing. So now for our variation table, with the domain of definition tells us that the curve moves from negative infinity to 1 to 3 to positive infinity. These are the values you can see here. But we equally know that there is a turning point when x is equal to 2. So that 2 must be included on the first column of this variation table. This is the 2 here. This is for the turning point. Then we know that x equals 1 and x equals 3 are vertical asymptotes. So we are going to use solid lines to indicate that the curve does not cross those values. However, x equals 2 is a turning point, so we are going to use a broken line to indicate this. Now use our gradient function to study these various regions. Between negative infinity and 1, is the curve increasing or decreasing? Let's take a number between negative infinity and 1. You can take 0, for example. We will not bother to use the denominator because it's always positive. So let's just work the numerator. So for 0, if you substitute 0 here, we are going to have minus 2 into minus 4, which is positive. The denominator is always positive. So positive divided by positive is positive. So in this interval, the curve is increasing. Now between 1 and 2, we can take 1.5. 2 times 1.5 is 3. 3 minus 4 is minus. So minus times minus is positive. So positive divided by positive is positive. So we still have a positive. In this interval, the curve is still increasing. So be very careful with this particular curve. Then as x tends to 2, we have a value of 0 because at the turning points, the gradient function is 0. Now between 2 and 3, we can take 2.5, right? So 2 times 2.5, that's going to give us 5. 5 minus 4 is 1. 1 times minus 2 is minus 2. So in this region, it is negative, or in this interval, it is negative. And for any value greater than 3, we have, let's take 4. 2 times 4, 8. 8 minus 4 is 4. So it's going to be negative in this interval as well. You have to be very, very careful and vigilant with this particular curve. Now here we know that the curve is increasing in this first interval. This interval is still increasing. Here it's decreasing, and here it's decreasing. Now from what value to what value? As x tends to negative infinity, this curve, the value of y tends to 0 from limits. So we have 0. As x tends to 1 from below, we had positive infinity. As x tends to 1 from above, we had negative infinity. As x tends to 0, as x tends to 2, that's at the turning point, we have minus 2, right? This is at the turning point. As x tends to 3 from below, 3 from below, we have negative infinity. 3 from above, we have positive infinity. And as x tends to positive infinity, we can see from this first limit tends to 0. So this is what we have this variation table. You can watch this one over and over again so that you have a clear clue of what's actually happening in the curve, okay? We can now sketch this curve. We have 3 asymptotes, x equals 3, x equals 1, and y equals 0. These are the 3 asymptotes. We have an intercept at 0 and 2 and 3. Then we have a turning point at 0 and 2 and 3. All right, the line is a bit up, but please, it's just drawing issues. Then we have a turning point somewhere. We have a turning point at 2 minus 2. 2 minus 2. Right, that's the other side of the curve. This is turning point at 2 minus 2. And so this can be represented like this. That's a turning point. And we know that it decreases in here. 1 from above is negative infinity. And 3 from below is negative infinity. So this is the curve of this function. We label these values. That is the curve of G. Okay, so this is the curve of G. The next question now, we're going to look at number 4, copyrighted content. Number 4, with this particular case now, the curve is going to alter a bit. With the previous one, there was a constant in the numerator, and you saw that the curve had existed in 3 separate regions. Now there is x in the numerator. Let's see how the curve behaves. If it's going to have that turning point again, or it's going to behave different. So the domain here is x should not be equal to 1, and x should not be equal to minus 2. So we have negative infinity to negative 2, negative 2 to 1, and 1 to positive infinity. We now get the limits as x tends to plus or negative infinity. Why am I writing this? Because as x tends to plus or negative infinity, you just take the highest degree in the numerator, that's x. Highest degree in the denominator, just take the highest degree in the first bracket times the highest degree in the second bracket. So x times x is x squared. X divided by x squared is 1 over x. So we have 1 over x here. So as x tends to infinity, normally, as the degree of the numerator is still less than that of the denominator, we know that the limit is 0 when you do this. That's why the limit here is 0. As x tends to negative 2 from below, we are going to have that limit to be negative infinity. As it tends to negative 2 from above, you have positive infinity. You can test negative 2 from below. Let's take like negative 3, the numerator will be negative. The denominator here will have negative, negative, and negative. Negative times negative is positive. Negative divided by positive is negative. That's why this limit is negative. Now take a number greater than 2. Take a number slightly greater than 2, okay? Do not go too far because you can see that 2 and 3 are very close. So a number slightly greater than negative 2, you can take negative 1.9. Note, negative 1.9 is greater than 2. Take negative 1.9 and fit here. This is going to be negative in the numerator. The denominator will be negative. This first bracket will be negative. And the second bracket is going to be what? Positive. So we have negative divided by negative is positive, divided by positive is positive. That's why this limit is positive. We do the same thing for x as it tends to 1 from below and above, and these are the limits we obtain. From the domain of definition, we have the vertical asymptotes to be x equals 1 and x equals negative 2 and y equals 0. Therefore, our center of symmetry is the average of the two vertical asymptotes, which is negative half and y value of 0. When x equals 0, we have an intercept at 0. So when x equals 0, y equals 0, so our intercept passes through the origin. Now we can get a gradients function. This is a rational function like we mentioned earlier. So when we differentiate, we are going to have the bottom constant. You differentiate the top, you have 1. So it's just going to be the bottom that's left here, minus top constant, differentiate the bottom. You have 2x plus 1. If you expand this as a quadratic or you use the product rule, you are going to have this. All this on the bottom squared. When we simplify this, we are going to have minus into x squared plus 2. So from here equally, I've factorized, I've expanded, simplified, and I'm factorized also. When you simplify, you're going to have negative into x squared plus 2. So this numerator is always negative from what we see here. And since the denominator is squared, the denominator is always positive. So therefore, this curve is strictly decreasing. So you can be asked to prove that this curve is strictly decreasing. And this is what you will do. I said the numerator is always negative. The denominator is always positive. Therefore, this curve is strictly decreasing. So from a variation table now, we have the domain negative infinity to negative 2 to 1 to positive infinity. And with this curve, there is no turning point because if you equate this to 0 and solve, there will be no value of x. So there is no turning point. Okay. Yeah, x squared plus 2, you equate to 0, you have x squared to be equal to negative 2. And that's going to give us complex roots, which is not in functions. So here, these are vertical asymptotes. So we have solid lines. Then this tells us that the curve is strictly decreasing. So it's decreasing here, decreasing. And this interval is decreasing. And here is decreasing. So everything is negative. So it's decreasing. We put down these lines that are moving downwards. But this one decreases to the turning points. Sorry, not the turning points, the origin where x is 0, y is 0. So to 0, or you can decide to leave it. And above here to negative infinity. So as x tends to negative infinity, we had 0 here. It moves to minus 2 from below, negative infinity. Minus 2 from above, positive infinity. To the point when x is equal to 0. So it passes through 0 at this point and moves down to negative infinity. 1 from below, we have positive infinity. And as x tends to positive infinity, from here we had 0. So this curve is going to be as follows. Those are the asymptotes. Then we have the horizontal asymptotes. And this is how the curve looks like. Here, it is going to move in some sort of a spiral shape and pass through the center of the Cartesian plane. So this is what happens. So whenever there is x9 in the numerator, you see now the curve now behaves like this. It does not have a turning point, and the curve moves from a region upwards to another one downwards. It can equally change like this depending on the values of x in the numerator can equally swap. All right, so this is what we have for this curve. In the next examples, we are going to be looking at how we can obtain the curve from the variation table and how we can obtain the curve from, we can obtain the function from the curve. Don't forget to subscribe and to leave your comments. Equally, if you have to study with us, you can join our affiliates program. We work with the GPP, or the GCE preparations platform is focused strictly on answering past questions for 20 years. The registrations always begin in September, and they focus on answering past questions for 20 years from that year backwards. They also focus on mocks and how to drill in exams, not just in mathematics, in physics and chemistry, in economics, in accounting, and all other subjects. It is a great platform. So you can just go to their website, www.thegpp.blogspot.com, and you register. The classes are not free. They do a paid registration of 1,000 francs, or you can talk about $2 for registration, and every month you pay $4 for each course. So that's just it. For Cameroonians, 1,000 francs for registration and $2 and $4, or 2,000 francs monthly for a course, and that's it. So I repeat again, www.thegpp.blogspot.com. All right, let me put it here. www.thegpp.blogspot.com. And equally, guys, please, if you like to support us or to promote our work, please, you can get to us on email and we can send our contacts or address so that you can support us financially or in any other way for these academic resources we are providing to you. It will be of great importance. It doesn't matter how small the thing the amount is, but it's going to go a long way to help us and to motivate us. So for patronage, you can get to us using the numbers that we have on our website, GCE Maths Panel.blogspot.com. Thank you. So let us move to this question now that okay, we are giving this function. This is going to be the last one, and the next two we are going to be taking what I just mentioned earlier on. So from here, the domain of definition is from negative infinity to 1 and 1 to positive infinity. At the limits, in this particular case, we have an oblique asymptote because the degree of the numerator is greater than that of the denominator. So I think it's good to touch this one before we move to the other two examples I just mentioned. So we are going to have an oblique asymptote, and for oblique asymptote, you're going to set the limit as x tends negative infinity here, highest divided by highest, that's going to give us x. So the limit is negative infinity. As x tends to 1 from below, this limit will give us negative infinity. As x tends to 1 from above, you're going to test, is going to give you positive infinity. And as x tends to positive infinity, we have positive infinity. This is just telling us the line y equals x maybe plus something is the equation of the oblique asymptote. So now let us determine the asymptotes. Now, whenever the degree of the numerator is greater than that of the denominator, you have to solve for the oblique asymptote. Okay? I repeat, whenever the degree of the numerator is greater than that of the denominator, you have to solve for the oblique asymptote. Here we can clearly see that the vertical asymptote is the line x equals 1, but you're going to use long division to obtain the equation of the oblique or the slant asymptote, oblique or slant asymptote. So you're going to say numerator divided by denominator. So we have x squared divided by x is going to give us x. So we have x. Now this x here times x is going to give us at this position x squared, and x times minus 1 is going to give us minus x. We subtract. So x squared minus x squared is 0. 3 minus, there's a minus sign here that is not written. 3 minus x. Or 3 minus, there is no term here in terms of 3, right? So 3 minus nothing is 3. And there is no x in the numerator. So 0 minus x is x. And 3 minus nothing is 3. Can we still divide? We divide by the highest degree, okay? So x divided by x is 1. So we have plus 1. Now plus 1 times all of these will give us x minus 1. We subtract again, and we are going to be left with x minus x is 0. 3 minus 1 is 4. So the questions that we have here is going to give us the equation of the oblique asymptote. So from here, what is the equation of our oblique asymptote? It is the line x plus 1. So the oblique asymptote is the line x plus 1. So this is how you obtain the oblique asymptote when you're given a rational function in which the degree of the numerator is greater than that of the denominator, okay? All right, guys, please don't forget this is our website link here. This is our website, www.the GCE Maths Panel .blogspot.com, or you can go to the GPP to register as you prepare for the GCE. You will not regret registering to this website to study with them. It's just like an online GCE school. For the intercepts, when x is equal to 0, we substitute here, we're going to have y to be equal to minus 3. And if y is equal to 0, there are no values for x. So we just move to the gradient function. And since this is a quotient, we use the quotient rule, the bottom constant. We differentiate the top, we have 2x minus the top constant, that is x squared plus 3. Differentiate the bottom, we have 1. All this on the bottom squared. So this will be equal to x squared when you simplify it, minus 2x minus 3. Now here we have to equate g prime of x to 0 to solve for x. So g prime of 0 of x equals 0 implies when we equate this to 0, we are going to have x squared minus 2x minus 3 equals 0. And when you solve for x using the quadratic formula or whatever factorization, you're going to have x equals minus 1 or x equals 3. Now we look for the corresponding values of y when x equals these values. So when x is equal to minus 1, substitute in this function. You will have minus 1 squared, which is 1 plus 3, 4. 4 over minus 1 minus 1. So 4 over minus 2, which is minus 2. So we have the point x, minus 1 minus 2. Note, in all my tutorials, I like to use A, B, and C for intercepts, and I like to use X, Y, Z for turning points. So X is the turning point here. And when x equals 3, substitute also here, you're going to have the value of y to be 6. So here we have 2 turning points in this curve. There are 2 turning points. Now we move to our variation table. From the domain of definition, we had from negative infinity to 1 to positive infinity. But from the turning points, we have the x values to be minus 1 and 3. We are going to use a solid line for the vertical asymptotes. And for the turning points, we're going to use broken lines to indicate. So we have one vertical asymptote and 2 turning points here. Now we look for this gradient function all through. So in this first interval, between negative infinity and negative 1, the function is going to be positive. Just take any number in between negative infinity and negative 1. It's positive here. Between 1 and 1, you can take 0. You start is negative. When x tends to 1, this is at the turning points, the gradient function is always negative. And then between 1 and 3, it is negative. X equals 3 is a turning point. So at this point, we're going to have 0 for the gradient function. And above 3, it is positive. So now these values tells us where the function increases or decreases. So here it's positive. So I'm going to a line going up. Here it's negative, line going down. Negative, going down. Positive, line going up. So it increases from what value as x tends to negative infinity. Y was negative infinity, right? As x tends to negative 1 is a turning point. Y is negative 2. X tends to 1 from below. 1 from below, we had negative infinity. 1 from above, we had positive infinity. X tends to 3, this is a turning point. Y is 6. And as x tends to positive infinity, what happened? Positive infinity, where's that positive infinity again? All right, y tends to positive infinity as well from limits. So we can sketch this curve now, and this is what we are going to have when you sketch this curve. And those are the oblique and slant asymptotes. Of course, this oblique asymptote, how do you do it? It's just like sketching a line. They say you should draw the line y is equal to x plus 1. So that's what you're going to do. So when x equal to 0, y is equal to 1. So this is a point 0, 1. Then another one, if x is equal to 1, just take any values and put and use. Okay. Now, for example, if x is equal to minus 1, y will be 0. So you link these 2 points now with a straight line. That's what you have. And the curve exists in this region and this region. And we know that we have turning points at minus 1, minus 2. This is the first turning point. This is minus 1, minus 2, as you can see from the curve. You indicate. And we could have another turning point at 3, 6. So when x is equal to 3, this is the line, the point here. And here you can see that y is 6. So we have another turning point here when y is equal to 6. And this curve exists on 2 sides. The center of symmetry here is 1, 2. And that's it. Okay, now let us look at curves from variation tables and functions from curves. Don't forget to subscribe and share this video, and you can join the gpp.blogspot.com to prepare for the GCE effectively. Now, what a beautiful question. You are given this curve, and they want you to study this curve. State the domain, the limits, intercepts, the vertical asymptotes, the oblique asymptotes, the turning points and the square between them, draw the variation table, and determine the curve G or the function G if it has this form. I love this question so much, guys. This is the last question in this tutorial, and I love it so much. So the first, in the domain of definition, you can see that the function is defined for all value of x except when x is equal to 1. So the domain is a set of all values of x excluding 1. So negative infinity to 1, and 1 from above to positive infinity. Now the limits, as x tends to negative infinity, this also tends to negative infinity. As x tends to 1 from below, we have negative infinity. As x tends to 1 from above, look, it's moving up to positive infinity. And as x tends to positive infinity, this thing is moving also to positive infinity. Now the intercepts, do we have an intercept here? I have an intercept here. This point is both a turning point and an intercept. Here, x is 0 and y is negative 2. X is 0 and y is negative 2, as you can see. Now, the B part of it states the vertical asymptote and the oblique asymptote. The vertical asymptote is the line x equals 1. And to get the oblique asymptote, we have to solve for it, because let the line be of the form y equals ax plus b, okay? y equals ax plus b, you can equally see at the end of the equation here, let the equation have this line, this form. So from here, we have to solve a and b, right? So if at the point 1, 0, you know, the curve passes at the point 1, 0 now, where I talk about this oblique asymptote, not the curve, oblique asymptote itself, because we are looking for the oblique asymptote, we want to look for the equation. It passes at this point where x equals 1, y is 0, this is the point here. So at the point of x is 1, y is 0, is substituting this function, we are going to have y is 0, so 0 is equal to 1 times a, is a plus b, so a plus b is 0. And it also passes another point again, here, 0, negative 1. So when x is 0, y is negative 1. X is 0, y is negative 1. We substitute here. So you're going to have all of this be 0, and negative 1 will be equal to b. So when we solve these two, we will have a to be equal to 1 and b to be equal to minus 1. Therefore, the equation of this oblique asymptote is the line x minus 1. So from here, we already have all of these things here now. Yes, this is it. So we already have. So we have looked for the oblique asymptotes. Then the next part of the question says state the turning points and distinguish between them. So the turning points, we have 0, minus 2, and you can start this is a maximum turning point. So we state that it's a maximum turning point. And this other one is 2, 2, and this one is the minimum turning point. So it's minimum turning points. So draw the variation table now. The variation table, we have from the domain of definition, we have negative infinity to 1 to positive infinity. We have turning points at 0 and 2. So we are going to use solid lines there. Use solid lines. I'm sorry, we have a vertical asymptote at 1. So we use a solid line. And for these 0 and 2, we have turning points. So we use broken lines. Now looking at the function from negative infinity to 0, the function is increasing. From 0 to 1, from x equals 0 to 1, let's see. So this curve is going down. 0 to 1 is decreasing. At x equals 0, which is the turning point, this y prime is 0. Then from 1 to 2, between 1 and 2, what's happening to this curve? This is between 1 and 2. It is moving from positive infinity downwards, it's reducing. So it's decreasing. And above 2, it starts increasing again. So it's increasing in this last interval. It's increasing. At 2, which is the turning point, it is 0. So here it is increasing. This interval decreasing, decreasing, and increasing. So increasing here at negative infinity, y was equal to negative infinity. At 0 is a turning point, y is negative 2. 1 from below is negative infinity. 1 from above, positive infinity. When x equals 2, we have y to be equal to 2, which is a turning point. And at positive infinity, we have positive infinity. Okay, now the last thing is to look for this g of x if it has this form. So we already have the values of a and b, right? So our g of x will be equal to x plus b plus c on x minus 1. And this will be equal to x minus 1 plus c over x minus 1. Why? Because we already looked for a and b. Already looked for a and b here. So we are just supposed to look for c here now. And how can we get this value of c? We can just take any of the intercepts like this one. This is an intercept and we substitute here. So at the point 0, minus 2, which is also a turning point, we have minus 2 be equal to 0 minus 1 plus c over 0 minus 1. And this gives us the value of c to be 1. Therefore, the equation of this curve or of this function will be x plus 1 over x minus 1. What a beautiful equation. And as simple as it is, what a beautiful equation. Yeah. This brings us now to the last question on this particular tutorial. Number 7, copyright its content. So we are being given this variation table. Let me put in the values. And with this variation table, we are being asked, we are being told that g of 0 is equal to -1. And what else to state the domain, the limits, the asymptotes, the monotonicity, the center, the parity, sketch the curve, determine the function if it has that form, that. So this is also another easy one. So we can start with the domain. We can say the domain is from negative infinity to 1, and from 1 to positive infinity. That is the domain. Then the limit as x tends to negative infinity is 2. As x tends to 1 from below is negative infinity. X tends to 1 from above is positive infinity. And as x tends to positive infinity, what do we have? We have 2. Those are the limits. And for the asymptotes, we have the vertical asymptotes. Vertical asymptote is x equals 1. Horizontal asymptote is line y equals 2. Okay. All right. So for the intercepts also, it has been given here 0 minus when x equals 0, y is minus 1. So we have the intercept 0 minus 1. And for the vertical asymptote is the line x equals 1. The horizontal is the line y equals 2. You can see it here. X tends to infinity, y equals 2. What is the monotonicity of this function? In this interval, it is decreasing. Here it's also decreasing. So y is strictly decreasing. Now, what's the parity of this function? I can say state the center. The center is given by the vertical asymptote and the horizontal asymptote. So we have 1 and 2. And for the parity, this function should be odd because it has a center of symmetry. If it does not have, we'll say it's not odd. Now we can sketch this curve, right? So let us sketch our curve. So when we sketch this curve, this is what you're going to have. So you take your time and do the sketching, okay? This is what you're going to have when you sketch the curve. It is on both sides. And I'm interested in this last part of it. So we are being told the limit as x tends negative infinity is 2, right? And you know that if you take the limit of this one as x tends negative infinity or positive infinity, that limit will be equal to a. You just have ax divided by x, which is a. So as x tends to negative infinity or positive infinity, that's going to give us a. And therefore means that from here, our a is equal to 2. So you can use limits to obtain this one. Secondly, now to get b, we can use the intercept. J of 0 is equal to negative 1. So j of 0 is equal to negative 1. We fit 0 here. We are going to have b over negative 1 is equal to negative 1. So our b is equal to 1. Therefore, the curve has this form. Just look at the equation, look very big, but it's very small and very fast. So this is the function. Guys, please don't forget to subscribe to this channel and to tell your friends about us. We equally have other channel, which is Maths 24 Super Channel. And for now, we are working with the GCE preparations program or platform called the GPP. So just go online and type the gpp.blogspot.com. You can register on the site because they've also contracted us to be working with them in teaching. They offer all the subjects for GCE and prepare you for the GCE. It doesn't matter the country in which you find yourself, you can still contact them either for personal class, for advanced level classes, ordinary level classes, and you can equally work as an agent, get GCE materials, and a lot more. Thank you so much. Stay tuned and don't forget to subscribe. We have been the GCE Maths Panel. In the next tutorial, we'll be looking at this type of functions. Bye.